Okay, for stress in saturated soil with an upward seepage, these are the important computations that we have to consider. Of course, we have an hydraulic gradient. In our previous discussion, hydraulic gradient, of course, is a vector gradient between two or more hydraulic head measurements over the length of the flow path. So for this illustration, there is a hydraulic gradient between 2 points. Of course, the hydraulic gradient between any 2 points is the slope of the hydraulic head between 2 points. So basically, for the hydraulic gradient here, because there is a head or a difference in elevation between 2 points, difference in elevation of the water surfaces between 2 points. So we have to identify our hydraulic gradient, which is actually equal to head all over the length of the soil sample. So for this one, our head is small letter h, the length of the soil sample is h all over 2. And at point A, so we can compute now the total stress. The total stress at point A for this illustration with the upward seepage, of course, is equivalent to at point A, we're trying to have at point A, this is point A, so the total stress would be H1 times the unit weight of, since this is water, times the unit weight of the water. Then, of course, our pore water pressure will be equivalent to, this is at point A, the pore water pressure is equal to H1 times the unit weight of the water. So therefore, our effective stress would be equal to 0 because we have same value for the total stress and the pore water pressure. So at point B, if we try to identify, that would be equivalent to, this is our point B. So this is point B, so that is the stress at point B would be equal to Z sub 1 times the unit weight of this portion plus H1 times the unit weight of the water. And the pore water pressure for that illustration would be equivalent to, that is at point B, the pore water pressure would be Z sub 1 plus H1 plus H of 1. So this is actually equivalent to, the pore water pressure at point B would be H1 plus Z sub 1 plus this one is connected to this pipe, so plus small h1 times the unit weight of the water, that is the pore water pressure. And the total, if there's, and the effective stress, you subtract the value of the total stress and the pore water pressure. So at point C, that will be equivalent to, this is point C, so the pore water pressure, the total stress at point C would be H2 times the unit weight on this layer plus H1 times the unit weight of the water. And the pore water pressure is equal to, if we're going to have the pore water pressure at point C, that will be equal to H1 plus H2 plus, this is the standpipe connected to point C, so this is plus H times the unit weight of the water. So that is the pore water pressure. And if you try to get the effective stress, you subtract total stress minus the pore water pressure, you have now the effective stress. And the seepage force per unit volume of the soil actually is equal to hydraulic gradient times the unit weight of the water. So for this example, consider the upward flow of water through a layer of sand in tank shown in this figure. For the sand, the following properties are given. So we have here E is equal to 0.40, our G is 2.67. So what is being asked here? To compute for the effective stress at point A, they calculate the effective stress at point B, calculate the upward seepage force per unit volume of the soil. So basically, if we're going to compute for the stress at point A, so we try to have this illustration. We're not given with the unit weight of the saturated sand, so we try to get the value for the saturated unit weight using this equation, since we are given with specific gravity with the void ratio, and of course we have the unit weight of the water. So we get now our saturated unit weight, 21.51 kilonewton per cubic meter. And if we were to get our hydraulic gradient I, which is H 1.5 over capital H2, which is 2, and it gives us 0.75. And you have to take note that the hydraulic gradient at H prime all over Z is equal to H all over H of 2. So that is constant. So if we're trying now to get the effective stress at point A, this is point A. What will be the effective stress? So we try to multiply 1 times the saturated unit weight, which is 21.51, plus our this portion, which is 0.7 times this is water, times the unit weight of the water. So we get 28.37 kilopascal. And the pore water pressure would be equivalent to, what will be our pore water pressure at point A? So that will be 9.81 times the height, which is of the water, which is 0.7 plus 1. This is connected to this standpipe, so plus H prime. So basically, for our H prime, we don't have the value for H prime, but we can solve for that using this equation. So we have here H prime all over Z, which is equal to I, and our I we have computed a while ago, which is equivalent to 0.75. So if we try to equate that one, so H prime is equal to 0.75 times 1, which is the value for Z. It gives us 0.75. That is now our H prime. And now if we try to have now the pore water pressure, so basically that is equal to the height, which is at point A, that is 0.7 plus 1. This is connected to this. H prime is 0.75. We have computed. So times 9.81, the pore water pressure is 24.03 kilopascal. And we can now get our effective stress. Subtract total stress. So we have total stress minus 24.3.03. So effective stress is 4.34 kilopascal. Now the effective stress at point B. If we try to get the effective stress at point B, this is point B, so that will be 2 times 21.51 plus 0.7 times 9.81, that is the unit weight of the water. So that is the total stress. Our pore water pressure at point B will be the height of the water, that is 0.7 plus 2. This is connected to this standpipe, so plus 1.5. So meaning to say the height of the water will be 0.7 plus 2 plus 1.5 times the unit weight of the water, which is 9.81. So we have now the value of 41.2 kilopascal. And to get the effective stress, we have 49.88 minus 41.2. It gives us 8.68 kilopascal. And the last one is to compute for the seepage force per unit volume of the soil. So we have the formula, which is I times gamma, I times the unit weight of the water, and our I is actually head all over the length of the soil, so that is actually equal to small letter h, this one is 1.5, that is the head difference in elevation. Now this between 2 points over the length of the soil, which is 2, so it gives us 0.75. Now our seepage force, that will be 0.75 times 9.81, the unit weight of the water, so it gives us 7.35 kilonewton per cubic meter. Now we move on to the stressing soil with a downward seepage. So for this one, the downward seepage, the water level in soil tank is held constant by adjusting the supply from the top and the outflow of the bottom. So this is an illustration for a soil with downward seepage. You have a tank, you have a soil within the tank, and the water level in the soil tank is being maintained in constant by adjusting in a constant manner by adjusting the supply from the inflow or from the top and the outflow at the bottom of the tank. So for this one, if you're going to analyze the stresses in soil for downward seepage, So we are going to have same concept of the stresses in soil with an upward seepage. You have to compute for hydraulic gradient. However, the difference here is the stresses. If you're going to get the stresses at point B and at point C, because a while ago we have here the illustration that since in upward seepage, since the water is going up, so the water on the standpipe will rise. However, in downward seepage, since the water is going down, so the water on the standpipe will lower. So basically, for this concept, we have hydraulic gradient, which is, of course, H all over H2 from this one. So this is our H all over this capital H2. And for the stress at point A, this is the stress at point A, so H capital H1 times this water times the unit weight of the water. And to compute for the pore water pressure, of course, at point A, capital H1 times the unit weight of the water. And if you're going now to compute for the effective stress at point A, you subtract the unit weight of the total stress minus the pore water pressure. Since we have the same value for this illustration, that will be equal to 0. So at point B, so here at point B, this is point B, the total stress would be unit weight on this portion of this layer times Z sub 1 plus capital H1, this one, times the unit weight of the water. So that is the total stress. If we're going now to compute for the pore water pressure, that will be the height towards point B. So that would be the height of the water, that would be capital H1 plus Z sub 1. This one is connected to this standpipe. So minus, since the water is going down, so that would be minus small h1. So we need to say at point B, the pore water pressure would be equal to the height of the water, that is capital H1 plus Z sub 1 minus small h1 times the unit weight of the water. So that is the pore water pressure. And to compute for the effective stress, you simply have to subtract. So total stress minus pore water pressure, you have now the value for the effective stress. For our point C, if you're going to have point C, what will be the stress at point C? So get the total stress at point C. So that will be capital H2 plus the unit weight of this soil layer plus capital H1 times the unit weight of the water. That is the total stress. Pore water pressure. Pore water pressure would be equal. At point C, the pore water pressure would be capital H1 plus capital H2. This is connected to this portion. So the water goes down at small letter h. So that will be at point C, the pore water pressure is equal to capital H1 plus capital H2 minus small letter h. And then all of those times 9.81, which is the unit weight of the water. And of course, to get the effective stress at point C would be the total stress. Effective stress at point C is equal to the total stress minus the pore water pressure, that is now equal to the effective stress at point C. So we move on to our sample problem. We are going to consider the downward flow of water through a layer of sand in tank shown in this figure. So this is the figure for our problem. For the sand, the following properties are given. E is 0.48, G is 2.7. We are going to determine the saturated unit weight of sand in kilonewton per cubic meter. Determine the effective stress at point A in kilopascal. Determine the effective stress at point B in kilopascal.